physics in winner 2014. I'd like to give a brief biography. Nakamura graduated from University of Tokushima 1977 with a degree in electrical engineering and obtained a master degree in same subject 2 years later. After which he joined the Nichiya Corporation, also based on Tokushima. He was awarded a Doctor of Engineering degree from the University of Tokushima in 1994. He left Nichiya Corporation in 1999 and took a position as Professor of Engineering at the University of California, Santa Barbara. The title of Professor Nakamura's keynote speech is Invention of Blue LED, Laser, and Solid-State Light.
Okay.
I'm sure the Professor Nakamura's keynote speech will be highly interesting to us. I'd like to call Nakamura-san.
So today I like to use the same graph which I basically used for the Nobel lecture, last December, and so basically Professor Akasaki and Professor Amano and and me, I got the Nobel Prize together, and the invention of the high efficient blue LEDs. So my talk is development of indium gallium nitride based double heterostructure high brightness blue LED and future lighting. So future lighting is I have one paragraph. Future lighting is should be laser lighting, and because current LED technology has some limitation, and it's called droop, but laser lighting has no droop. So expect in the future. All of the lighting would become laser-based lighting. So this is the outline, and it's okay. Yeah. So LED. So this is introduction of LED. No pointer. So basically, so LED is basically composed of four layers. There's the substrate. And the substrates. On the substrates, there are N-type gallium nitride, and the second layer is active layer. We call active layer, or some people call emitting layer, and the P-type layer. So in the case of for blue LED using a nitride-based material, there are no active layer, there are no P-type layer in 80s and 70s. So if we could invent active layer and the P-type layer, we could win Nobel Prize. So basically, Professor Akasaki Amano invented the P-type layer earlier than me. So that's the reason they got Nobel Prize. So in my case, I improved the P-type layer. Also, I invented the active layer. So I worked for 2 layers. So that's the reason I got the Nobel Prize. So this is a basic structure of LED, and so basically substrate is sapphire, and there's N-type gallium nitride and active layer and the P-type layer. So this is now commercially available blue LEDs. These blue LEDs are mainly for use for the white LED lighting. Also, for consumer, for all of LCD TV, use this LED as a backlight by making white. So how to make white? Because right now, white LED has the largest, biggest market, and just basically blue LED, and we use phosphor to change the color to make white. So basically, blue LED used to make white by using phosphor, and so that's and white LED is the biggest market for for lighting application. All kind of mobile devices use LCD displays. They need backlight. Also TV, all TV use LCD, and so they need the backlight. So they all backlight now use white LEDs. So white LED means they have to use blue LED, and So this is, for example, mobile phone. Mobile phone, use LCD, So they needed a backlight. But before invention of Blue-LED, they couldn't make a mobile device. They couldn't make cell phone, they couldn't make iPhone, they couldn't make iPad, because there are no display. Because at that time, available lighting source was the incandescent bulb lamp or fluorescent lamp. Fluorescent lamp, you need a huge battery, also incandescent bulb lamp. Only after invention of Blue-LEDs in Nichia in 93, cell phone company started making cell phone. And then next is iPad, iPhone, those things. And also interesting is automobile headlamp. So I think now LED is used for the automobile headlamp, but already some automobile companies laser lighting. So because laser lighting is a future lighting technology. So this is efficiency of the conventional lighting and the LED lighting. So long time ago, people used kerosene or oil lamp. So but the efficiency is very small. Efficiency is only 0.1 lumen power. This is the efficiency, and the higher the better. And in also, I don't know, it's small. Yeah. And also 19th century, incandescent bulb was invented by Thomas Edison, but efficiency is only 16 lumen power. And in 20th century, fluorescent lamp was invented, and the efficiency of fluorescent lamp is 70 lumen power. And basically, in white LED was invented in 96 by Nichia Chemical Corporation. And the now efficiency of white LED is 300 lumen power. This is R&D level. So mass production level is half. So I think 150 lumen power. So you can see the efficiency is very high using white LEDs. Also, you have to compare the lifetime of LED. White LED lamp is almost at least 30 or 40 years. So if you use LED lamp at home, you don't need any maintenance. Also, how much energy saving is, in the United States, so if people change the conventional lighting using LEDs, as a current pace, by 2030, on the United States, they can save 40% of electricity concerned about the lighting application. And this is almost same as number of 30 oil power plant. So if people use, current by replacing conventional lighting with a current space, so we can eliminate at least 30 oil power plant by saving the energy for lighting. So also carbon dioxide emission is also 185 million tons of carbon dioxide is also eliminated. So it's a huge energy and also energy reduction. This is only for United States. So all over the world, I think this multiplied 5 times, 6 times, I guess. So next, I'd like to about how to invent the blue LEDs in my case. So I started the blue LEDs in '89. So at that time, there are 2 kinds of material to develop blue LEDs. One is zinc selenide, and another material is gallium nitride based materials. And so zinc selenide based materials they are good substrate to grow zinc selenide. It's called gallium arsenide. So gallium arsenide substrate could be used to grow zinc selenide, and with no lattice mismatch. No lattice mismatch is atomic arrangement almost the same among the 2 materials. So it means no crystal defect when grow zinc selenide on gallium arsenide. But in the case of gallium nitride, only available substrate is sapphire. So in this case, lattice mismatch is 16%. So it's a huge difference of the atomic arrangement between gallium nitride and sapphire. So it means when we grow gallium nitride on sapphire, there are a huge number of dislocation or crystal defects, order of 10 to the 9th. It's a huge crystal defect. So this is an example. When we grow gallium nitride on sapphire, you can see dark line. This is dark line. It's called threading dislocation. This is a crystal defect. So in this, in this scale, this dark line should be 0 to make high efficient LEDs. It was common sense in 80s, about 70s. In the 80s, 70s, in order to make LEDs, efficient LED and reliable LEDs, this line defect should be 0 in this scale. You can see this is tensionized. It's a crappy material. So that's the reason in 80s, 70s, basically nobody tried this material because this is the biggest problem. In the case of zinc selenide, almost nothing. It's a beautiful crystal. So that's where I started the Blue LED 89, and so zinc selenide on gallium arsenide, crystal quality, distributed density is less than 10 to the third. So basically all of scientists who work for Blue LEDs, they selected zinc selenide. That's 89. In the case of gallium nitride on sapphire, crystal defect is more than 10 to the 9th per square centimeter. And so not to 0, but only few researchers working in the world. In the United States, I think only 1 or 2 groups, and in Japan, 3 groups. In Europe, I don't know, maybe 1 group. So it's a small number of people. But in the case of zinc selenide, oh my gosh, I don't know how many people are working. Maybe at least 1,000 groups in the world. And so in Japan, there's it's the biggest conference. It's called Japanese Society of Applied Physics in this field. It's called the JSAP conference. It's the biggest conference in Japan in this field. So in 89, so zinc selenide session, number of audience is 500, more than 500. And the gallium nitride session, I think a typical number is 5. So including a session chair and the speaker and the audience. Audience is 3 over 2, including me. So this is a typical number, right? Zinc selenide, oh my gosh, in this room, still not enough. Zinc selenide session. So, so also gallium nitride, also all people, gallium has no future, gallium nitride people have to move zinc selenide material, no. So in 89, but I selected gallium nitride. So the reason why I selected gallium nitride is from 88 to 89, I went to University of Florida as a visiting researcher 1 year. And so at that time, I worked together with PhD students at the University of Florida. And all the PhD students asked me, do you have a PhD degree? I said, no, only I had a master's degree. And then next day asked me, have you published a scientific paper? I said, no, 0. And then those students treated me like a technician. So here in the United States, United States scientists means they have to have a PhD degree. No PhD degree means a technician. So it's a huge difference in the United States. But in Japan, no difference. No. In Japan, no PhD, no difference. Everything is same. But in the United States, it's a big difference. So 1 year later, I came back to Japan, and my dream became to get a PhD degree. So in that case, so I thought about, which one is better to publish a paper. At that time in Japan, if I could publish at least 5 scientific papers, I could get a PhD degree. It's called the paper degree. In the United States, it's impossible. But at that time in Japan, just publishing paper, you could get a PhD degree. It's called the paper degree. So my dream was to submit at least five scientific papers. But if I select zinc selenide, huge number of papers, it was impossible because I never published papers. But if I select gallium nitride, almost 0 papers. So it's easy to publish paper, Any kind of result I expected I could publish paper, But I never expected I could invent blue LEDs. So that's the reason I selected gallium nitride. And then, so I started the gallium nitride blue LED research in 89. And so initially, So I had to grow gallium nitride crystal. So method is only MOCVD. So we had to use MOCVD to grow gallium nitride crystal growth. So already, another Nobel laureate, Professor Akasaki and Amano already working for the gallium nitride crystal growth. This is their MOCVD reactor. And so they work for university. They were working for Nagoya University. So they use this MOCVD, but this MOCVD is a lot of problem. So I had to invent the MOCVD myself. So initially, I purchased a commercially available MOCVD from a Japanese MOCVD company. It cost $2 million US. And I started the gallium nitride growth. But for a couple of months, I worked for gallium nitride growth, but there are no crystal growth. Even if there are crystal growth, color was black. So good gallium nitride crystal means the color should be transparent. So several months later, I made a decision. I had to modify this MOCVD. So I spent almost 1.5 years to modify the MOCVD reactor. And finally, I got this reactor. I named the two-flow MOCVD. And so this is a great MOCVD ever. So until I could this invention, I could publish any papers. I could not publish. I could submit any patent. But after this invention, every 2 or 3 months, I could write a patent and the papers. So it means that every 2 or 3 months, I could invent something in the field of gallium nitride. Because this reactor is best in the world, still best in the world. That is why Nichia is making still high efficient LED also laser diodes. This reactor is a key invention. Because the reactor is great, it means any crystal growth, clarity is best in the world. So after this invention, everything is easy. So big reason, before my invention, always the professor and Akasaki showed the best result in the world. But after this invention, always I could show the best result in the world in this field. So for example, undoped gallium nitride growth, so professor and Akasaki got the mobility. Mobility is higher, this is electron mobility, higher the better. So no buffer layer is 50, and using aluminum buffer, they got 450. But in my case, using two-flow MOCVD, no buffer is 200. And I invented gallium nitride buffer, and mobility 600. Mobility higher the better. So next invention is a P-type gallium nitride. So this is the key. So if usually so this is as grown of magnesium doped GaN. So as grown magnesium doped gallium nitride should be P-type, but always semi-insulated. So nobody could understand. And but in '89, Professor and Akasaki and Amano found if they irradiate the electron beam for magnesium doped GaN, they got P-type gallium nitride, means the low resistivity P-type gallium. But they couldn't understand the reason. But I could clarify the reason in '92. So basically, we use ammonia gas for the gallium nitride growth. So ammonia gas is dissociated to the atomic hydrogen. So atomic hydrogen is combined with magnesium active substance. It's the magnesium hydrogen complex. So magnesium acceptor is passivated by atomic hydrogen. So that is called hydrogen passivation. But using thermal annealing, we can remove the atomic hydrogen from the magnesium hydrogen complex, and we got P-type gallium nitride. Or also using electron beam, we can remove the atomic hydrogen from magnesium hydrogen complex. So that's the reason we got the P-type gallium nitride using thermal annealing. So also I invented thermal annealing to make P-type gallium nitride. So now all of LED company, laser company in this field are able to use thermal annealing to activate the magnesium P-type gallium nitride. So basically, I invented the P-type gallium nitride for all of LED laser company. Also, I clarified the reason. This is the physics, So this is the physics, So this has been a mystery of the gallium nitride for past 20 years because nobody could get P-type. They couldn't understand the reason. So I clarified the reason. So next is LED. And so basically, left side, so Professor Akasaki and Amano got the P-type gallium nitride by electron beam irradiation. Also, they got the PN junction LED and PN gallium nitride homojunction LED. And this is, there are no active layer. So efficiency of LED is almost zero. Zero. You can see a little bit emission on the dark room. So this is Professor Akasaki Amano invented this PN gallium nitride homojunction because there are no emitting active layer. But to make a high efficient LED, we need a double heterostructure. Double heterostructure means we have to insert the active layer. Active layer is emitting layer. So this, for example, Professor Alfred and Professor Kurama got Nobel Prize by invention of the idea of double heterostructure, because the double heterostructure is very important to make a high efficient LED, also all kind of electronic devices. So this is a comparison of homojunction LED, double heterostructure LED. So homojunction LED is efficiency very small because minority can diffuse. But in the case of double heterostructure, all of injected carriers is confined active layer, so we can make very high efficient LEDs. So that is a double heterostructure. But for active layer, so people had worked for to make a high quality active layer for a long time. In 70s, 80s, nobody could make the active layer material. So active layer material should be indium gallium nitride. Indium gallium nitride. So if we can make a very high good quality indium nitride, we can make a double heterostructure. Indium nitride should be active layer. So, but the indium nitride growth is very, very difficult in 80s, 70s. Several groups tried to grow indium nitride, but all people failed. So basically, most active group was Dr. Matsuoka's group. He now is a professor of University of Sendai, and his group got the best result, but only they observed the band-to-band emission at low temperature, at liquid nitrogen temperature. At room temperature, basically no band-to-band emission, basically no emission. So this is the best result. But this material could not be used for the active layer because there are no band-to-band emission at room temperature. But I told you, using 2,4 MOCVD, in our group, we got the very strong band-to-band emission for blue and violet, also green, in 92. So this, I told you, so 2,4 MC is the best reactor. So we could make a big breakthrough of the active layer. We got to the very strong of the band-to-band emission using indium nitride for the first time in 92. So now we can make double heterostructure. So, so in 92 we developed a double heterostructure LEDs, and active layer is indium gallium nitride, and active layer, indium nitride active layer is sandwiched by N-type gallium nitride and P-type gallium nitride. So we can make very high efficient, very high power blue LEDs in 93. Also same time we started the commercialization. Out power is 1.5 milliwatt at 20 milliwatt. At 2 milliwatt is fine. But the PN homojunction is a microwatt order, no PN homojunction. So this is a Nobel Prize citation. So you can see Nobel citation is the same, basic structure LED is a substrate, N-type GaN, and the active layer, and the P-type gallium nitride. So also in 95, also we developed the indium gallium nitride, first indium nitride quantum well, blue, green, yellow LEDs. So this is now basic structure of currently commercially available blue, green LEDs. All of LED companies use this structure to make LEDs, because this kind of active layers, quantum well, indium gallium quantum well, and everything. Also, in 96, we developed the first violet laser diode in 96 using indium gallium nitride quantum well active layer. So this is the first first laser diode, violet laser diode, So this violet laser diode now used for Blu-ray DVD, you work for consumer electronics, so Blu-ray DVD is, without this laser diode, they couldn't develop the Blu-ray DVD. Also now this laser diode also used for the laser projector by changing the color to blue, laser projector, So indium gallium nitride is a key material because so this shows the efficiency of various LEDs as a function of the dislocation density. Dislocation density is the crystal defect density. So you can see conventional compound semiconductors such as gallium arsenide, gallium phosphide, gallium arsenide phosphide LEDs. Those LEDs, the efficiency become very small when the dislocation density is more than 10 to the third or fourth. But in the case of indium gallium nitride based LEDs, the efficiency is still very high, even at the dislocation density is order of 10 to the 9th. So indium gallium nitride is a key material to make high efficient LEDs in spite of the huge number of crystal defects. Because 10 to the 9th is a crazy number of crystal defects. I told you, in 80s, 70s, all people had to consider how to reduce the dislocation density less than 10 to the third. Because at that time, people are working for gallium arsenide, indium phosphide-based LED laser diode. So at that time, dislocation density should be less than 10 to the third. But nitride, indium gallium nitride-based material, dislocation density even at 10 to the 9th. Still, LED is very efficient. But the laser diode is different. The laser diode is current density a little bit high, so we have to reduce the dislocation density. But so that's why the indium nitride is so efficient in spite of huge number of dislocation. So basically, this is just idea. Professor Chichibu of University of Tohoku now proposed localized states in 96, localized states. But indium gallium, there is alloy fluctuation. So there are some indium rich region and indium poor region. So indium rich region, they form the localized states. So injected carriers recombine radiatively at the localized states, which is caused by indium rich region. So just this is idea. Still, we don't know the exact reason, but the indium gallium nitride is a key material and the mysterious material to why the indium gallium based LED is so efficient in spite of a huge number of dislocations. So that's the historical figure. So this shows the luminous efficiency of the red, blue, and green LEDs. So basically, red LED was invented in 1960s by Professor Nick Horoniak of University of Illinois, and the efficiency of red LED gradually increased. And so basically, InGaN based LED, blue efficient LED invented in 93. Then the efficiency of the indium gallium double head LEDs increased dramatically, and the white LED is the same. And basically, but this view graph always we don't write about the MIS LED developed by Maruska in 1973, or the PN gallium homojunction LED by Akasaki in 1989, because these LEDs are so dim. So so basically we don't write this one, but so basically, so this shows a contribution towards the high efficient blue LEDs. So basically, P-type gallium nitride is achieved by electron beam, by Professor Akasaki Amano in '89, first time. So but that's the reason they got Nobel Prize, because at that time nobody could get P-type gallium nitride. So in my case, P-type gallium nitride, I developed P-type by using submarine. Also, I clarify the mechanism why we got the P-type gallium nitride by submarine and the electron beam radiation. It's caused by hydrogen passivation. And also, in my case, most important invention is the indium gallium nitride emitting layer or active layer in '92. So N-type layers are available, and also buffer layer. Also, Professor Akasaki Amano invented the aluminum buffer layer in '85 to improve the crystal quality of gallium nitride. But in my case, I invented the gallium nitride buffer layer in '91. So that's the contribution. Also, this shows the history of the gallium nitride growth and the indium gallium nitride based devices. So you can see in '85, and Professor Akasaki Amano invented the aluminum buffer layer to improve the crystal quality. Also, 89, they invented P-type gallium nitride using low energy electron beam irradiation treatment. So that's why they got Nobel Prize, because they did the first time they obtained the first P-type gallium nitride for the first time. And so in my case, I started the gallium nitride growth in 91. So in my case, the most important thing is 92, P-type gallium nitride using submarine, also discovery of the hydrogen passivation. This is the mechanism of the P-type gallium nitride. Also 92, indium gallium nitride. We got the first high-quality indium gallium nitride which showed the bound passivation in 92. Also 95, we made the first high-efficient blue LED using the indium gallium double structures. Also, green LEDs 95. Also, we got the first laser diode, violet laser in 96, and the silver operation. Also, in 96, so last one, Nichia started the mass production of white LEDs using high-efficient indium gallium blue LEDs. So that's the reason now. So since 96, white LED available. And then all companies started making backlight for LCD display and lighting application. It's okay, I will skip. I want to skip, this is too much energy consumption. So how much energy is consumed in California? So California, so this is in California, and California among all of electricity, so lighting consumes 35%, and heating, cooling, ventilation relatively large. So 35% of the electricity is consumed for the lighting. And but this is the conventional lighting. So using LEDs, this one should be almost 1/10 as a final goal, 1/10, because the efficiency of white LED is 10 times high efficient than the conventional incandescent lamp. In comparison, fluorescent lamp ends twice. And huge. And I told you so. By 2030, we can, eliminate at least 30 oil power plants by changing the conventional lighting with LEDs, with a current pace. And so this is a satellite image at the nighttime of the Earth. So nighttime is the white region is lighting, lighting. So in the United States, I told you, we can eliminate 30 oil power plants. So worldwide, you can guess, almost 5 times or 6 times. You can eliminate oil power plant. Also, solar powered LED lighting. So this region has no electricity, red region, no electricity. So no electricity means nighttime, no lighting. And but so people had to use the kerosene lamp, or you can say kerosene lamp. But this kerosene lamp emits a lot of carbon dioxide, and also the very dangerous, especially it causes fire, And but now using white LED and plus battery, also plus solar cell. So daytime, using solar cell, they can charge the battery, and at nighttime they can operate white LEDs using the battery. So now they can use very safe lighting using white LEDs. And this one is also very cheap. Because the kerosene lamp, they have to spend how much? They have to spend almost $100 per year to buy kerosene oil every year. They have to buy. But white LED plus battery plus solar cell, its total cost is this one. You can see green one. It's $8. By buying $8. This is solar cell and battery and the white LEDs. Battery lifetime is still not good. That's the reason electric vehicle is still not good. The battery lifetime is only 3 or 4 years. So that this 3-4 years, just spend $8, they can get lighting. So it's very cheap. Kerosene is every year they have to spend $100. And but the white LED lifetime is 50 years, 100 years, and the solar cell is also, I think, same order. The problem is the battery lifetime too short. So we need more reliable battery, for everything. And I think this one. So this is so UCSB vision, and so you can see the drawing. So this is efficiency of LED as a function of the current density. So LED, you can see red one. LED, with increasing current density, efficiency drop sharply. Red one. So in the case of LED, we cannot increase the current density to make a bright light, to get a bright light, because it's called droop. This is called by auger recombination, because the auger recombination is the intrinsic material problem. So we cannot solve this problem. But in the case of laser diode, you can see with increased current density, still efficiency is getting higher, and keep the highest efficiency until the current density up to 2 kiloampere, more than 2 kiloampere. So using laser diode, we can make very, very bright lighting source. Or, so you can the also chip size. In the case of LED, we have to reduce the current density less than 0.1 amperes per centimeter, 0.1, 0.2. So in that case, to make bright light, we need a big chip emitting area for LED, because we can't increase the current density. So in order to make this bright, total chip area is huge. But in the case of laser diodes, current density, we can increase the current density dramatically, so we can make, using tiny chip like this, we can make very bright lighting. So it means, so tiny chip means we can reduce the cost dramatically, and processing become very, very simple, tiny. So smaller the better for processing. So I think future lighting should be laser lighting. So already, some automobile company already using laser lighting for the automobile headlamp. Because the laser lighting also very directional light. But for this, I'm talking about all kinds of general lighting too, in order to reduce the cost. So that is our university UCS vision. So I use this novel lecture. So I'd like to thank Nichiya, founder of Nakamura and the current president Asia, and all of my colleagues of the R&D department between 89 and 99, all employed in Nichiya Chemical Corporation. Because all of today I talked about all of the researchers achieved at Nichiya Chemical Corporation before 99. And also I moved to UCSB in 2000, and I'd like to thank Henry, Chancellor, Dean, and all of my professors, colleagues. Thank you. That's it. So, okay, so.
Do you have any questions?
Dr. Nakamura, thank you very much for your speech and clearly your dedication and vision to this project over the decades. Do you have any advice to us as engineers and to young engineers? What other frontiers do you see that you would like to tackle, you'd like to see others succeed in very soon? What challenges lay ahead, like your challenge with silicon nitride?
So challenges for this nitride-based lighting. I tell you this challenges of this my final final graph, and so the challenge is right now LED lighting is it's very expensive, because for example incandescent bulb is like 50 cents, but the same performance of the LED lighting is like $20, $30. So everyone complains. So that's a challenge. So that's the reason I propose this laser lighting. Laser lighting is a tiny chip. Everything very simple, tiny. So smaller the better to reduce the cost. So I think, right now the challenge is the cost, and price. But I think using laser lighting, they are high possibility. So.
Thank you, sir.
Any questions?
Professor Nakamura, thank you so much for your presentation. I really enjoyed the part that you mentioned about your honest reason why you choose to go into gallium arsenide nitride compared to the other one. My question is, where do you draw your inspiration from when you mentioned that you were working 1.5 years on the MOCVD? Where do you draw your inspiration from before you make the breakthrough?
I don't know your question. So basically, I joined the Nichia Chemical Corporation in '79 after graduating the University of Fukushima. So first thing is I worked with the conventional infrared and red LEDs for 10 years. And basically no result, but I learned all kind of technology of LED. And in '89, I switched the new material of gallium nitride to develop blue LEDs. And so for first 10 years, I had to work for at that time, first 10 years, I had basically no budget. At that time, the company was almost bankrupt, So no budget. Even for at that time, I had to work with the crystal growth, gallium arsenide, gallium phosphate. I needed a reactor, furnace. And I asked that it cost 10,000, 20,000 US dollars. So I asked the manager, boss, please buy this reactor. But they said, no, zero, no budget. So I had to furnace reactor myself. For past 10 years, I had always like a mechanical engineer. Always I had to, welding, those things. Always I had to the machine shop, to make all kind of reactor. And so that's the reason. So I switched the blue LED research in '89. For first 1.5 years, 2 years almost, I had to modify the MOCVD reactor. So without past 10 years experience to work for the machine shop, I couldn't modify the MOCVD reactor. So I think the first 10 years experience, I don't have no result, but the first 10 years was work is very, very important for my life, especially for machine shop technology.
Okay, thank you. Could I have a follow-up question? What do you think is the most rewarding part of your career beside the Nobel Prize?
The career beside Nobel Prize. Very good. Oh, I don't know. I had no idea. I no idea. I don't know. But no prize, I don't like the citation of the no prize. I hate it because when you check the Nobel Prize homepage, they talk about why we got Nobel Prize, their citation. They didn't mention anything about indium gallium nitride. I told you, indium gallium nitride is most important to make high efficient LED laser diode. Without indium gallium, nobody can make emitting device. But the Nobel citation, they didn't mention anything about indium gallium, zero. So I am so mad. So I think the Nobel Prize is the worst prize for me, worst prize, in the view of the citation. But except the Nobel Prize, I have listed all, how many? Maybe 20 very great award or prize. All of the other awards talk about the indium gallium nitride's most key invention. But only Nobel Prize didn't mention anything about it. So I don't know what's going on. So basically, Nobel Prize is not so important for me, almost the worst prize for me in the view of citation. But the popularity is the Nobel Prize is no comparison. But the citation, I don't know why it didn't mention it. I don't know.
I'm a very big fan of those different types of lights and the lights that you invented, and I use them. But sometimes I wonder, are there differences in the biological effect, how the lights, the lights from different sources affect us biologically? I know, for example, that people say that don't read books at night just before you go to sleep using an iPad, because that type of light actually transmits to your brain signals that means to the brain wake up, not go to sleep. So it's better to read paper. So I wonder if there is any research that was done to assess the various biological effects of these different types of lights on human beings and animals too.
Yes. Oh, yeah. For example, Philips has worked a lot about the biological effect of the, by changing lighting. So especially color. No. Yes, totally you're right. So blue is very good for the wake up. So blue lighting is the best for the morning for wake up. So, so before sleep, before going to bed, blue lighting is worst. You cannot sleep. So, yeah, totally right. I'm not. There's a huge effect of biological things. By changing a color lighting source. I'm not familiar so much, but you should, talk with the Philips people. They have started a lot of things, those things. So especially because using LEDs, we can change the color, or we can get all kind of colors. So Philips also developed depending on the time from the morning to night, they made a special lighting to change the color. So morning is blue light, and nighttime is blue. Yeah. So yeah, just like with Philips people. Yeah.
Thank you very much. Thank you very much. Very interesting speech.
Okay. Okay. Thank you. Okay.